Hello everyone. Today we're going to discuss a new topic called torsion of shaft. So torsion of circular shaft. So here the first topic is pure torsion. What is this pure torsion? A member is said to be in a state of pure torsion if it is subjected to only torsional movement. So what is the torsional movement? Very simple. If you consider a circular shaft like this, okay? If you consider a circular shaft like this, its cross section is a circular one. If the member is subjected to axial. Okay, this is the axial load. That is longitudinal force, and this is the lateral force. And along with that, if you consider this one, this is nothing but a torsional force. Okay, torsional force, and it will result in a twisting of shaft. Twisting of shaft. So this is what they are saying. If it is subjected to only torsional movement, okay, this is a torsional movement, not accompanied by any other forces. So first one is this one, another one is this one, not accompanied by any other forces such as bending and axial force. So because of this force, we are going to have a bending moment, and because of this force, we will be having a extension of a shaft, that means elongation of a shaft. So we are not having any of these forces. Okay. So any of these forces, we are having only this torsional force. Because of this, the shaft is going to twist. That is nothing but a pure torsion. That means a member is subjected to only torsional movement. Okay. Then we can say the member is in pure torsion. Now here we are going to assume certain assumption. The first one is the material of the shaft is uniform. Okay, the material of the shaft is uniform, not tapered. So second assumption is the material of the shaft obeys Hooke's law. As you all know that the stress is directly proportional to strain within the elastic limit. That is the Hooke's law. And the stresses are within the elastic limit. So obeys Hooke's law and the stresses are within the elastic limit. That is the second assumption. The third one is the twist along the length of the shaft is uniform. Along the length of the shaft, that means, so if you consider this is the total length of the shaft, if you consider a twist, okay, so the twist will be uniform throughout its length from here to here. Okay, it's going to be uniform. The twist along the length of the shaft is uniform. So next one is the cross section of the shaft, which are uh, plane and circular before twist remains plane after the twist. Okay, the cross section remains same even after twisting. That is the fourth assumption. The fifth one is all radii which are straight before the twist remain straight after the twist. Okay, so before applying the torsional moment, the radii, whatever the radii it is having, that radii remains same even after the application of the twisting movement or torsional movement. When the shaft undergoes twisting, okay, so the radii remains same. That is the fifth assumption here under pure torsion. Okay, so after discussing this, what is meant by pure torsion and what are the assumptions we are going to make in case of pure torsion, we will get into this torsion equation, which is very important. So torsional equation. What is this torsional equation? So for that, we need to have this diagram. Okay, so this diagram, very, very simple, right? So just draw one vertical line. Okay, it is a cantilever condition. Just draw one rectangle. So after that, just draw one circle like this. Okay, just draw one circle from this center. From this center, just draw one line, horizontal line, and this is the center. And from here to here, the reference point. Okay, before applying the twisting moment. Now, when you apply a twisting moment, okay, so now when you apply a twisting moment, okay, when you apply a twisting moment like this, okay, this is T, or a torque, when you apply a torque, so the new position of it will be from here to here. Okay, just assume this as A and this as B before the application of this twist or torque. So this is O and this is P, initial position. When you apply this torque P, so the new position of B is B dash. Okay, so twisting moment. So it is going to have a twisting moment. So B is changing to B dash. So here it is B dash. B dash. Now you please carefully observe the angle between this is phi The angle between this is theta. What is phi and what is theta? So here it is given. Phi is shear strain, theta is angle of twist. Okay, so please be careful. So here we have a initial position AB. After the application of this C torque, it is going to have a new position. AB will become AB dash. So AB will become AB dash. That is the new position. The angle made by this BA, this B, A and B dash, it is phi. It is phi. That is nothing but shear strain. And here in the cross section, okay, in the cross section, the angle made by BOB dash, it is nothing but theta. The theta is nothing but angle of twist. Okay, that's what this diagram will be. So here explanation is given. Consider a solid circular shaft of length L, of length L. The radius R from here to here, the radius is R, fixed at one end. So fixed at one end and subjected to pure torque P at the other end. That means on the other end, it is subjected to torque. Okay, at the other end, it is subjected to torque. So that's shown in the figure. Let the line AB, as I said, that let the line AB on the surface of the shaft will be distorted. Okay, will be shifted to AB dash. Will be shifted to AB dash after the application of the torque. So when the torque is applied, the position of AB will be changed to AB dash. So thus the cross section will be twisted. This is a cross section. The cross section will be twisted from OB to OB dash. The angle made by this OB and OB dash, it is nothing but theta. That is nothing but angle of twist. Okay, so here they have given from the diagram, you need to observe. So the angle BAB dash, the angle BAB dash is phi, that is nothing but shear strain. So here in the cross section, the angle made by BOB dash, it is theta. The theta is nothing but angle of twist. The angle made by BOB dash or OB dash, that is nothing but theta, which is called as angle of twist. Now you need to consider the shear strain at the outermost surface. The shear strain, whatever we have considered at the outer surface will be equal to distortion per unit length. Distortion per unit length. That is nothing but change in length per unit length. Change in length to the original length. So that how we are going to consider that? Very simple. So tan phi. What is tan phi? So here phi. Okay, shear strain. Whatever we have considered. So this will become a right angle triangle. So like this. Okay, so this is P, this is A, and this will be B dash, and this angle made by is phi. Okay, so from this diagram, so tan phi. Okay, so tan phi will be equals to, so this opposite side divided by adjacent side. Okay, opposite side by adjacent side. What is opposite side? B dash. Okay, the initial position to final position. That is nothing but distortion at the outer surface divided by length of the shaft. Length of the shaft is what? AB. So B dash divided by AB is nothing but opposite by adjacent, which is nothing but tan phi. So that will be equals to B dash divided by L. B dash divided by L. So tan phi we are going to consider it as phi because it is a very small angle. So that's why tan phi is almost equal to, not exactly equal to, it is almost equal to phi. Phi is nothing but shear strain, that will be equal to B dash divided by L. So call this as equation number 1. Okay, call this as equation number 1. Next. So from the figure, okay, so from the figure, what is that figure? So here we have considered one circle, right? So from this center, so if you draw one line, this will become O and this is B. And from here to here, it is B dash. So this angle is nothing but theta. Okay. From here to here, what is that? It is a radius R. Okay. Now from the figure, arc BB dash, that is from here to here, arc BB dash is equal to, okay, is equal to So OB, this distance OB into theta. Okay. So RBB dash can be found out by using this OB into theta. Okay. OB into theta. OB is nothing but radius. Okay. From the center till the outer surface, the distance is radius R into theta as it is. RBB dash is equal to OB into theta. OB is nothing but R. Theta remains as it is. Now substituting this RBB dash, the value of BB dash into this equation 1. Okay. Into this equation 1. What is BB dash? It is R theta. Now phi will become R theta by L. Call this as equation number 2. Okay. Very simple. Now you know that shear stress, tau is the shear stress. So shear stress, how we are going to define? So G, what is G? G is the shear modulus. Okay. Modulus of rigidity, shear modulus or modulus of rigidity, that will be equals to shear stress by shear strain. So shear stress by shear strain. So from this, shear strain will be equals to tau by G. Shear strain, just cross multiplication. Phi will be equals to tau by G. So call this as equation number 3. Now please observe what is equation number 1. Shear strain is equal to BB dash divided by L. Equation number 2. Shear strain is equal to R theta by L. Now again shear strain is equal to tau by G. That I'm going to call that equation number 3. Okay. Now from equation 2 and 3. Equation 2 and 3. So in the left hand side we have phi. Just replace this with respect to this. Okay. So or else reverse. So phi here we have. You can substitute the value of tau by G. So phi is equal to R theta by L. Phi is nothing but tau by G. Tau by G is equal to R theta by L. So from this, tau by R is equal to G theta by L. G theta by L. So this is the equation. If Q is the shear stress at any radius, for example, if you consider a circle, okay, diameter of a shaft. So from this center, except this outer surface, in any other radius, if you consider the radius is small r, for this, the shear stress will be Q. Shear stress will be Q. But if you consider the radius as capital R at the outer surface, the shear stress will be tau. Please remember, if you consider a small r, the shear stress will be small q. If you consider a capital R, which is at the outer radius, okay, so for that, shear stress will be tau. So here what we are assuming that if Q is the shear stress at any radius R from the center of the shaft, then tau by R is equal to G theta by L is equal to shear stress by radius. Okay, shear stress by radius. So here what they have given, the shear stress tau in the shaft is proportional to the radius of the shaft. Okay, it is directly proportional to radius of the shaft. The shear stress is 0 at the center. Okay, so the shear stress will be equal to 0 at the center and maximum. So shear stress will be maximum at the outer surface. Okay, at the outer surface of the shaft. Now we are going to derive the relation between torque, shear stress in a solid circular shaft. Relation between torque, that is capital T, and shear stress, tau, in a solid circular shaft. Okay. So for that, we need to consider this small circle. Okay. So just consider a circle. So this is the center. So apart from this circle, any other radius. Okay. Just consider any other radius as a ring. Okay. So from this center till this ring, the radius is R. Okay. So from this center till the outer surface, it is capital R. So this ring thickness is given by small dr. Okay, small dr. And from here to here, it is a diameter. Okay, so this is the basic construction or a diagram of this for this relation. Now, consider a solid circular shaft subjected to pure torque. Solid circular shaft, as you all know that we are going to consider a solid circular shaft which is fixed at one end and the other end it is subjected to torque. Okay, its cross section is circle. So consider a solid circular shaft subjected to pure torsion or torque T. Consider an elementary ring. This one is the small elementary ring what we have considered. Thickness is dr. Thickness is dr at a distance r. At a distance r, small r, from the center of the shaft. And at this point, that means at the small r, the shear stress will be, what is the shear stress? In the last class, we said that at small r, the shear stress will be small q. Okay, the shear stress at the radius is q. So this dA, what is dA? dA is the area of the ring. So area of the ring, because we are not considering the area of the outer surface, we are considering the area of a ring. So that is small dA. So that is nothing but 2 pi r into dr. 2 pi r into dr. What is df? Df is a force on the ring, force acting on the ring. What is that force? Stress into area. You all know that stress will be equals to force by area. So from that, force will be equals to stress into area. What is stress? Shear stress. We are considering the shear stress. So that is small q. What is area? It is a small area of the ring. That is dA. Q into dA. What is the value of dA? So from this equation, that is 2 pi r into dr. So the equation will be df is equal to q into 2 pi r into dr. Now coming to this, what is dt? The torque. Okay, the torque acting on this elementary ring. Torque will be equal to force into distance. What is force? Force is df, distance is r, radius, elementary ring. So elementary ring is at a distance of small r from the center. That's what we are considering. df into r, force into distance. What is df? Sorry. So what is df? So from this df, it is q into 2 pi r into dr. Just substitute that. 2 pi r into dr into q multiplied by r. So this r into r will become 2 pi r square. Q remain as it is dr. Q into 2 pi r square into dr. That is the torque which is acting on the small elementary ring. Small elementary ring. Now integrating this equation, which equation? This one. So integrating this equation from 0 to r, that is from the center till the outer surface, the radius will be capital R. Integrating from 0 to capital R, so capital T, torque will be equals to q and 2 pi. Okay, take outside the integration. So integrating from 0 to r square into dr. So now from this, what is q? Q is a shear stress, right? So q by r is equal to tau by r. So from this, q is equal to tau by r into r. Tau by r into r. So just substitute that value, tau by r into r, in the place of q. Okay. So 2 pi as it is. This q will become tau by r into r, integrating from 0 to r square into dr. Now, this 2 pi r, okay, 2 pi tau divided by r, this r multiply inside, r square will become r cube into dr. Now, integration of r cube is r to the power of 4 divided by 4. Actually, it is small r to the power of 4 divided by 4. When you apply this limit, capital R, the small r will become capital R. R to the power of 4 divided by 4. Okay. Now this r and this one get cancelled. So r to the power of 4 will become r to the power of 3. and this 2 ones are 2 twos are. Okay. So this equation will become like this. Pi r cube divided by 2 into tau. Pi r cube divided by 2 multiplied by tau. Now, r is equal to d by 2. Radius is equal to diameter by 2. So r cube, that is d cube, 2 to the power of 3. Okay, 2 to the power of 3 will be equals to 8. So d cube divided by 8 into tau. So the final equation is d is equal to pi d cube by 16 into tau. Okay, so please remember this equation. This equation is very much important in problem. So t is equal to pi d cube divided by 16 into tau. Please make a note of this equation. Now, it's not yet over because we need to derive the relation between t and tau, right? So this is one of the equation, but we have not arrived at the final equation still. So next t is equal to tau by r into pi r to the power of 4 divided by 2. So here take r is equal to d by 2. When you substitute that value in this equation, it will be pi d to the power of 4 divided by 16 into 2. That will become pi d to the power of 4 divided by 32. So this value will be j. J is nothing but polar moment of inertia. So t is equal to tau by r into j. Okay, so from this equation, t by j is equal to tau by r. So that will be equals to g theta by L. G theta by L. That is the final torsional equation. T by j equals to tau by r equals to g theta by L. So here T is the torque, J is the polar moment of inertia, tau is the shear stress, R is the radius of the shaft, G is equal to modulus of rigidity. So theta is the angle of twist, L is the length of the shaft. Okay, so these are the terminologies we are going to use in the torsion of shaft. Next is power transmitted by the shaft. So here the equation P is equal to 2 pi nt by 60. So here you need to be careful. In the denominator, if you are considering 60, so this P value you need to substitute any other. For example, if power is 60 kilowatt, so that time you need to consider 60 into 10 to the power of 3. Otherwise, if we have consider in the denominator as 60,000, okay, so this P value you need to consider as only 60, not 60 into 10 to the power of 3. So 60 value, I'm assuming that, okay, for giving an example, I'm assuming this value. It is not fixed. Understood? So please be careful while solving the problem. So 2 pi nt divided by 60, that is the power transmitted by the shaft. So where n is the speed, p is the torque. Next, polar section modulus, that is nothing but Zp. Zp is equal to J by R. J is the polar moment of inertia. Zp is the polar section modulus. J by R, pi d to the power of 4 divided by 32 divided by R. What is R? R is d by 2. So from this equation, polar section modulus will be pi d cube by 16. Pi d cube by 16. Next one is for hollow shaft. Okay, for hollow shaft. That means, so in the hollow shaft, you will be having a outer diameter and inner diameter. So for that, Zp is equal to J by R naught, means outer radius. So J is pi d to the power of 4 divided by 32. In this case, you need to consider both outer and inner. D to the power d naught to the power of 4 minus di to the power of 4 divided by d naught divided by 2. So from this, pi divided by 16 into d naught into d naught to the power of 4 minus di to the power of 4. This is the formula for polar section modulus for a hollow shaft. Next one is torsional rigidity. It is also called as stiffness of a shaft. That is nothing but Kt. Kt is equal to T by theta. T is the torque, theta is the angle of twist. So that will be equals to Gj by L. So this formula is also very important because many times they are going to ask in the problem to find out the torsional rigidity or stiffness of a shaft. In that case, you need to use this formula T by theta or Gj by L, depending upon the values given. Okay, so in the next class, we are going to start with the numericals. Thank you.